What if everything you've ever known, every atom, every planet, even the very fabric of your body, has a hidden twin you can never see? A silent reflection of our universe, woven not from shadows, but from an entirely different kind of matter, mirror matter. It doesn't glow. It doesn't shine. It doesn't interact with light or touch or time as we know them. And yet, some physicists believe it might be everywhere, around us, within us, shaping galaxies, forming stars, even holding the key to dark matter, missing neutrinos, and the very symmetry of the universe. Why do the laws of physics treat left and right differently? Why do neutrinos disappear without a trace? Could there be entire mirror galaxies rotating in perfect silence, influencing ours through invisible gravity? This isn't science fiction. It's a real scientific mystery, rooted in quantum theory, parity violation, and the deepest unsolved puzzles of modern physics. And it forces us to ask, are we living in just one half of reality? In this documentary, we'll explore the eerie symmetry that nature broke, the strange experiments hinting at another world, and the bold idea that our universe might be just one side of a cosmic mirror. Along the way, we'll dive into the bizarre quantum behaviors, the hunt for hidden particles, and the haunting possibility that somewhere out there, or maybe right here, another version of you exists, made of mirror atoms in a mirror world. The question is no longer, is there something out there? The question is, have we only been looking at one side of the mirror? Nature has always seduced us with symmetry. From the crystalline elegance of snowflakes to the spiral geometry of galaxies, we've come to expect balance, a universe that mirrors itself in every corner. And for a long time, physics confirmed that belief. The idea of symmetry wasn't just aesthetic, it was embedded in the equations that describe our world. One of the most sacred of these principles was known as parity symmetry. It held that the laws of physics are indifferent to left and right. Flip a system like a mirror, and the universe should behave exactly the same. For decades, this belief stood unchallenged. It seemed impossible to imagine a universe that would behave differently if everything were mirrored. But the 20th century had other plans. In 1956, a quiet revolution began when two theoretical physicists, Sung-Deo Lee and Chen-Ning Yang, dared to ask a question no one had seriously entertained before. What if the weak nuclear force, the interaction responsible for certain types of radioactive decay, does not respect parity? It was a radical idea, and it needed proof. That proof came in the hands of Xian Wu, a brilliant experimental physicist who conducted a now-famous experiment using cobalt-60 atoms. She cooled these radioactive atoms close to absolute zero and aligned them using a magnetic field, then observed the direction in which they emitted electrons during decay. If parity symmetry held, those electrons should have emerged equally in all directions. But they didn't. The electrons favored one direction. Specifically, they were emitted opposite to the direction of the nuclear spin. This wasn't a subtle imbalance. It was a clear, decisive violation of mirror symmetry. The implications were staggering. A core law of physics had revealed an unexpected bias, a preference for leftover right. The universe, it seemed, wasn't entirely symmetrical after all. For physicists who had built their understanding on the foundations of symmetry, this was deeply unsettling. How could the cosmos, so balanced in other ways, allow one of its fundamental forces to break the mirror? Rather than dismiss this as a mere anomaly, some scientists began to wonder, was the weak force truly asymmetric, or was it just incomplete? What if the apparent imbalance was only because we were seeing just half the picture? And what if, somewhere beyond the reach of our detectors, there existed a hidden counterpart, a reflection of our universe where the weak force behaves in the exact opposite way? From that daring thought emerged the idea of mirror matter. At first, it sounded like speculative science fiction, but the concept was mathematically elegant and philosophically profound. For every particle in our known universe, electron, proton, neutron, there could exist a twin, a mirror particle with identical mass and lifetime, but with opposite-handed interactions. Together, our particles and their mirror counterparts would restore parity symmetry across a larger framework, our visible universe, plus a parallel, invisible one. This mirror world wouldn't be a fantasy realm with castles in the sky. It would be governed by mirror versions of the same fundamental forces. Mirror photons, mirror atoms, mirror chemistry, all existing in a sector completely hidden from ours, except, possibly, through gravity or incredibly weak quantum-level interactions. It wouldn't reflect light or matter in any familiar way. We wouldn't be able to see it, touch it, or bounce signals off it. And yet, it might be as real as everything we know. What's astonishing is that this hypothesis doesn't require rewriting all of physics. Instead, it simply extends the standard model, doubling its content and offering a deeper symmetry that resolves the imbalance observed in the weak force. It's like realizing that a lopsided coin is only one half of a matched pair. You just didn't know the second coin existed. The idea gained traction because it didn't just explain parity violation, it offered tantalizing connections to other cosmic mysteries. Could mirror matter be responsible for the missing mass we call dark matter? Could it explain why neutrinos seem to vanish, or why certain anomalies appear in particle experiments without clear cause? These are not idle speculations. They are questions grounded in unresolved data, the kind that mainstream physics continues to wrestle with. But at its core, the mirror matter theory is about the limits of human perception. It challenges our assumption that what we see is all there is. If a parallel sector exists, invisible yet gravitationally significant, then we've only been interacting with half of reality. The other half is silent, dark, elusive, but possibly more common than our own. There could be mirror stars, mirror planets, even mirror life. They would never emit light in our spectrum. They would never react with our atoms. Yet they could be there, drifting beside us in perfect isolation. The psychological shift this idea demands is enormous. We've long embraced Occam's razor, the principle that the simplest explanation is usually best. But simplicity is subjective. What seems complicated to the human mind may be elegant from a cosmic perspective. The broken mirror of the weak force might not be an error or an oddity. It might be a clue, a cosmic breadcrumb leading us to the realization that symmetry does exist, but not where we expected it. The irony is poetic. The mirror matter hypothesis suggests that the only way to restore symmetry is to embrace duality. Reality, in this view, is not a single-threaded narrative, but a duet, a conversation between two worlds that rarely, if ever, speak to each other. One is bright, tangible, and loud. The other is dark, intangible, and silent. Yet both are governed by the same deeper rules, balanced not in isolation, but in union. And what makes this even more haunting is the mirror's refusal to reflect. If this parallel sector is real, it doesn't bounce back photons. It doesn't cast shadows. It doesn't shimmer on the edges of telescopes. It hides, not by deception, but by design. It's the kind of hidden that doesn't want to be found. Still, hints may be scattered throughout the universe, in the way galaxies rotate too fast, in the puzzling behavior of neutrinos, in subtle anomalies in experimental physics that keep defying explanation. Maybe these are echoes, ripples, or whispers from a world we cannot see. A world that, if real, might answer some of the deepest questions we've ever asked. What is the true shape of the universe? Why does anything exist at all? And could something invisible be watching us, mirroring us, moving beside us, forever unreachable, but forever present? This is the enigma of the broken mirror. And perhaps, just perhaps, the key to understanding it lies not in what we see, but in what we've never been able to see at all. In the vast architecture of physical law, quantum mechanics reigns as both the rulebook and the riddle. It gives us the strange theater of superpositions, entanglements, and particles that are also waves, all stitched into a fabric of uncertainty that governs the smallest building blocks of reality. And yet, for all its predictive power, quantum theory has never claimed to reveal everything. It tells us how particles behave, but not necessarily why the universe favors one version of that behavior over another. Mirror matter isn't a mere storytelling device or theoretical whim. It emerges logically from the attempt to restore symmetry to the universe. For every known particle in the Standard Model, electrons, quarks, photons, and beyond, the theory posits a counterpart, a mirror electron, mirror quark, mirror photon, and so on. These counterparts would have identical mass and quantum numbers, but they would interact through their own mirror versions of the electromagnetic, weak, and strong nuclear forces. In essence, it would be a shadow universe with the same complexity as our own, running parallel but almost entirely disconnected from the matter we know. The only bridge, perhaps, would be gravity or other extremely weak portals, so faint they have remained invisible in all our experiments so far. And yet, their fingerprints may already be on the cosmic canvas. The logic behind mirror matter isn't just rooted in restoring symmetry, it also offers surprising solutions to several cosmic puzzles. One of the most enduring of these is the mystery of dark matter. Galaxies spin faster than their visible mass would allow. Gravitational lensing bends light more than observable matter can account for. Cosmic structures hold together in ways that standard physics can't explain unless there is an invisible mass holding the strings. Dark matter has remained elusive, unresponsive to light, radar, and all electromagnetic signals. But what if dark matter isn't exotic or fundamentally alien? What if it's just familiar matter in a hidden mirror form? If mirror matter interacts with our world only through gravity, it would behave exactly as dark matter does, quietly shaping galaxies, fueling cosmic evolution, yet refusing to shimmer in any telescope's eye. This is what makes mirror matter Not just a curiosity, but a viable candidate in the race to decode the dark side of the cosmos. And the implications stretch even deeper. The neutrino, an almost massless, ghostly particle, is one of the strangest inhabitants of the quantum world. It oscillates between types, disappears and reappears, and defies detection in maddening ways. Some anomalies in neutrino behavior have even hinted that they may be slipping into a hidden sector, possibly into their mirror counterparts. These hints, still unconfirmed, have kept physicists intrigued, and experiments like those at Fermilab, Gran Sasso, and Ice Cube humming with anticipation. If mirror neutrinos exist, they could revolutionize not just particle physics, but cosmology itself. And if neutrinos can oscillate into mirror forms, could other particles do the same under certain conditions? The idea is tantalizing because it would mean that the barrier between our world and the mirror world isn't absolute. It's porous in the subtlest, most quantum way possible. Mirror matter also proposes a new lens through which to examine the early universe. At the moment of the Big Bang, the universe exploded from a singularity, expanding in all directions and generating matter and energy in a searing, chaotic birth. But the equations governing that event are symmetric. They don't distinguish between forward and backward, between matter and antimatter, or even between our universe and a hypothetical mirror one. Some cosmologists suggest that mirror matter may have formed alongside regular matter, birthed from the same singularity, but evolving along its own track. If true, this could help resolve another long-standing problem, the matter-antimatter asymmetry. According to theory, the Big Bang should have created equal amounts of matter and antimatter, which should have annihilated each other completely. Yet here we are, surrounded by matter with hardly any antimatter in sight. Mirror matter offers a workaround. Perhaps the missing antimatter isn't missing at all. Perhaps it resides in the mirror world, maintaining cosmic balance in a hidden way. The beauty of the mirror matter theory lies in its symmetry, but its mystery lies in its elusiveness. Why haven't we detected it directly? The answer may be as simple as the design of our instruments. Our detectors are built to catch electromagnetic interactions, but mirror particles would be blind to our photons. Our machines search for charged particles, but mirror particles might not react to electric or magnetic fields at all. Only gravity, that most ancient and least understood of forces, would link us. And gravity is notoriously hard to isolate in a lab. So the silence of mirror matter may not be an absence, but a veil, one we haven't learned to lift. Some researchers have proposed clever experiments, oscillating neutrons in magnetic traps, for instance, or searching for tiny deviations in atomic transitions. But so far, the mirror remains intact. It neither cracks nor reflects. It simply doesn't respond. Yet even this quietness is instructive. If mirror matter exists, it might not just be out there in space. It could be here, around us, right now. Mirror stars could orbit galaxies alongside visible ones. Mirror planets could exist in the same solar systems, invisible companions to worlds we already know. Mirror meteors might have passed through Earth without leaving a trace. Even mirror life is not beyond consideration, though such a life form would be governed by mirror biochemistry and mirror evolution, inaccessible to every method we have for detection. Such life would not just be alien, it would be undetectable, except by inference. Perhaps civilizations of mirror beings observe their own cosmos, theorizing about strange gravitational effects that they too cannot explain, effects caused by our visible matter, tugging invisibly on theirs. The concept of mirror matter forces us to think beyond the scope of our sensory apparatus and even our instruments. It is a metaphysical challenge as much as a scientific one. It suggests that the universe may be infinitely more complex than what we observe, and that what we take as emptiness might actually be full, just not with the kind of matter we recognize. It invites us to see reality not as a single continuum, but as a layered structure, with multiple coexisting domains, each obeying its own version of natural law. These domains may interact faintly, or not at all, but their existence would redefine what we mean by everything. The multiverse theory often gets the headlines, but mirror matter could be a subtler, more scientifically tractable step in that direction, another realm, not another universe. Even if mirror matter remains undiscovered for decades, its theoretical value persists. It provides symmetry, explanations, and predictions that no other current theory does, all while remaining consistent with known physics. That balance of boldness and plausibility makes it uniquely compelling. It is not magic. It is mathematics extended one step beyond the visible. And in that step, there lies a possibility that all of reality, even the reality we pride ourselves on understanding, is just a partial view. The rest is still cloaked in quantum shadow, not because it's hiding, but because we haven't yet developed the vision to see it. Among the strangest hints that something lies beyond the known frontier of matter comes not from distant galaxies or massive black holes, but from the subatomic realm of the elusive neutrino. Long dubbed ghost particles for their almost supernatural ability to pass through solid matter without interaction, neutrinos are both everywhere and yet practically undetectable. Every second, trillions stream through your body, born in nuclear reactions from the sun, distant supernova, or deep within the Earth itself. But what makes them so enigmatic isn't just their invisibility, it's their behavior. Unlike any other known particle, neutrinos oscillate. They change flavors mid-flight, transforming between electron, muon, and tau neutrinos, a phenomenon that defies classical expectations. And buried in these oscillations are anomalies, discrepancies that suggest neutrinos might sometimes vanish into something we haven't yet accounted for. That something could very well be their mirror selves. Experiments over the past 2 decades, from LSND to Miniboon and beyond, have recorded results that don't quite fit within the standard model's tidy framework. These anomalies aren't consistent enough to constitute proof, but they persist with a strange kind of regularity. One of the most compelling interpretations is that the missing neutrinos are oscillating not into other known types, but into sterile states, particles that don't interact through the weak force. And what could be more sterile than a particle that belongs to a mirror universe, with no interaction in our sector, except perhaps through gravity or fleeting quantum mixing? This raises the possibility that neutrinos might be the key that unlocks access to the mirror world, not by directly revealing it, but by disappearing into it. Such a process wouldn't be science fiction. In fact, it's predicted by many models that attempt to unify the forces of nature or to extend the standard model with additional symmetry. Mirror matter fits perfectly into these frameworks, offering a quiet, mathematically coherent explanation for otherwise baffling data. And while neutrinos are the best known candidates for such oscillations, they may not be alone. Other particles, particularly neutral ones like neutrons, may also exhibit hidden oscillations under specific conditions. The idea is deceptively simple. Isolate a free neutron in a magnetic trap, shield it from all external interactions, and wait. If neutron disappearance occurs beyond known decay channels, it might imply a jump into the mirror sector. Though difficult to execute, this kind of experiment is actively underway in multiple labs around the world. Beyond laboratory experiments, the cosmological implications of mirror oscillations are profound. In the early universe, when temperatures were unimaginably high and all forces were unified, even the mirror and ordinary sectors might have been in thermal equilibrium. But as the universe cooled and expanded, they would decouple, growing increasingly isolated. Still, traces of that early connection may linger in subtle quantum effects. Residual mixing between mirror particles and their counterparts today could contribute to unexplained phenomena like the precise ratio of light elements observed in the cosmic microwave background or the dynamics of galaxy formation in the early epochs of the universe. These are not abstract claims. They are predictions that can, in theory, be tested. Moreover, if mirror neutrinos exist, they could affect the evolution of stars. In particular, during core collapse, supernova, among the most violent events in the cosmos, neutrinos carry away most of the energy. But if some of that energy leaks into mirror neutrinos, the observed neutrino burst would be weaker than expected. Intriguingly, certain supernova observations already show discrepancies in the timing and intensity of neutrino detections, though data is limited. Future detectors, like DUNE and Hypercamiocande, might offer the resolution needed to determine whether such leakages are real. If confirmed, it would mean that mirror matter doesn't just shape galaxies from the shadows. It participates in the birth and death of stars. Then there's the quantum question of entanglement. If mirror particles exist and occasionally mix with standard particles, could this mixing extend to entangled systems? Could we find that entangled pairs, separated by vast distances, experience decoherence not through environmental interaction, but via hidden oscillation into mirror partners? This speculative idea is still in its infancy, but it reflects a growing realization that quantum systems are more open and more vulnerable than previously believed. In an age where quantum computing and quantum communication are beginning to reshape technology, understanding such hidden channels isn't just a theoretical pursuit. It may become essential. Even the behavior of cosmic rays and high-energy particles might hold clues. When cosmic rays collide with the atmosphere, they generate showers of particles, including neutrinos. But if mirror matter exists, some interactions could yield mirror particles that we cannot detect directly, skewing our interpretation of these events. Similarly, strange deficits in particle count, energy imbalance in collider experiments, or unaccounted for momentum transfers might be whispers of mirror interactions. Physicists often refer to such events as missing energy signatures, and while many explanations exist, from instrumental error to exotic particles like axions, the mirror world remains a persistent candidate. What makes this idea so compelling is not its drama, but its silence. Mirror matter doesn't scream for attention, it hides. It obeys all known laws in its own sector and communicates with ours only through the weakest threads of existence. And yet, those threads might be strong enough for us to follow. It's a strange reversal. The very thing that makes mirror matter hard to find, its silence, might be what allows us to detect it. Because the universe, like any great mystery, is not silent. It echoes. Through ghost particles and hidden oscillations, it hints. It stutters. It deviates just enough to say there is more. And in those deviations, we might find not only a new understanding of matter, but a new understanding of what it means to observe, to measure, and to exist in a universe that may never fully reveal all of itself. If ghost particles, like neutrinos, can vanish from our detectable world through oscillations, the natural question that arises is, where exactly do they go? It's not enough to say they simply disappear. In physics, disappearance often implies reappearance somewhere else. An accounting must be made. The energy, the identity, the information, none of it just evaporates. What if, in those fleeting moments, these particles are not ceasing to exist, but are instead transitioning into a parallel framework of reality, a hidden mirror version of our universe? The mirror universe hypothesis proposes just that, a duplicate cosmos, a reflection of our own, composed not of speculative fantasy, but of rigorously postulated particles and laws. It's not a mirror in the metaphoric sense, but quite literal in its symmetry. For every fundamental particle we know, electron, proton, neutron, there exists a mirror twin. These mirror particles aren't antimatter, and they're not the superpartners of supersymmetry. They're distinct entities governed by mirror versions of the same forces. A mirror neutron would have the same mass as a regular neutron, the same spin, the same decay properties, but it would interact only with other mirror particles and mirror forces. This symmetry, if real, would double the particle zoo and render the standard model only half the story. The concept originates from a deeper desire for balance in nature. Physics has long been driven by symmetry, conservation of energy, charge, momentum. Yet, certain processes violate symmetry in subtle ways. The weak nuclear force, for example, violates parity. In simple terms, some interactions look different when viewed in a mirror. This was a shocking revelation in the mid-20th century and suggested that the universe has a preferred handedness. But if mirror matter exists, then parity could be restored on a grander scale. Our universe would be left-handed, the mirror universe right-handed, and together they'd form a complete symmetrical whole. The asymmetry we observe would merely be a projection of a higher symmetry that encompasses both realms. But how could such a universe remain hidden? The key lies in the forces that govern interaction. Mirror matter, according to the hypothesis, does not couple to our electromagnetic field. It doesn't interact via the strong or weak nuclear forces that bind our world together. The only force it shares with us, perhaps, is gravity. That one slender thread may be the only whisper of its existence. This is why mirror matter is a compelling dark matter candidate. It checks all the boxes: non-luminous, non-absorbing, stable, cold, and massive. It gravitates, but it doesn't glow. If it exists in abundance, it could form stars, galaxies, and even black holes, but in a mirror sector, invisible to our telescopes and sensors. Some theoretical models even suggest that mirror matter might clump similarly to ordinary matter, forming mirror planets and mirror life under entirely parallel chemistry. In such a world, Mirror hydrogen would bond with mirror oxygen to form mirror water, just as ours does. Mirror stars would burn mirror hydrogen into mirror helium, perhaps even producing mirror neutrinos that, under the rare right conditions, might mix with ours. Entire civilizations might exist in the mirror realm, unseeable not because of distance, but because of interactional isolation. The profound implication here is that the universe could be populated in ways we've never imagined, inhabited not only by what we see, but by what we fundamentally cannot. And yet, the division might not be absolute. Certain models allow for tiny kinetic mixings between the mirror photon and the standard photon, which could permit mirror particles to possess minuscule electric charges, so small they would be nearly undetectable, but not zero. This opens the door to exotic experimental possibilities. In highly sensitive detectors designed to pick up weakly interacting particles, faint signals might arise from these mirror interactions. Small deviations in expected results, anomalies that currently defy explanation, may in time be reinterpreted as signs of mirror matter brushing against the membrane of our visible world. There's also the intriguing concept of portals, regions in space or in controlled laboratory conditions where quantum tunneling or magnetic anomalies might enable transitions between sectors. Experiments involving ultra-cold neutrons have tried to detect such transitions. By placing neutrons in traps with specific magnetic configurations and monitoring their decay patterns, researchers are testing whether some neutrons vanish, not by decay, but by transitioning into mirror neutrons. While no definitive evidence has yet been found, certain statistical irregularities continue to provoke interest. These are the kinds of experiments where the outcome might not be a dramatic light show, but a subtle dip in numbers, a quiet anomaly, a fingerprint of something vast. Cosmology also offers fertile ground for the mirror universe. During the Big Bang, if both sectors were created simultaneously, they would have evolved together, initially sharing the same thermal environment. However, if the mirror sector had a slightly lower initial temperature or decoupled earlier due to the absence of interactions, it would cool and evolve more slowly. This divergence could explain why we don't see mirror radiation in the cosmic microwave background or mirror signatures in primordial nucleosynthesis. But their gravitational imprint would remain: subtle distortions in galaxy rotation curves, excess gravitational lensing in regions where no visible mass exists, or even the unexplained stability of galactic clusters that seem to require more masses than we observe. The mirror universe may also offer solutions to long-standing cosmological puzzles. One of these is the baryon asymmetry problem. Why does the universe have more matter than antimatter? According to some formulations, if both ordinary and mirror matter were produced in equal but separate quantities, with CP violation occurring in opposite directions in each sector, then the overall symmetry would be preserved, but one universe would become matter-dominated and the other antimatter-dominated. That could explain our existence without requiring finely tuned violations of known physics. Even entropy might find a mirror reflection. If time's arrow points forward in our universe due to increasing entropy, could it point backward in the mirror universe? Could mirror time flow in reverse from our perspective, forming a temporal symmetry across the cosmic divide? Though speculative, such ideas tap into the profound questions of causality and time's directionality that haunt the foundations of physics. If entropy governs our perception of cause and effect, then perhaps the mirror universe holds a reversed perception where their future mirrors are past and events unfold in a deeply alien logic. The hypothesis also intersects eerily with quantum mechanics. Consider the possibility that entangled particles, upon decoherence, aren't merely interacting with a noisy environment, but leaking information into the mirror sector. Such a mechanism could preserve unitarity while explaining why quantum collapse appears irreversible. It would recast the measurement problem, not as a metaphysical mystery, but as a physical exchange, information siphoned into a mirrored quantum reality. The implications for quantum computing and encryption would be staggering, raising questions about security and coherence in systems that are no longer as isolated as we thought. As theories grow bolder, some suggest that black holes themselves could serve as conduits between the two sectors. The matter falling into a black hole in our universe might emerge as mirror matter in the mirror universe, and vice versa. This could preserve information and resolve the black hole information paradox, a tantalizing prospect that suggests black holes might not be the ultimate vaults of reality, but bridges between worlds. Even Hawking radiation could carry mirror signatures, distortions in expected spectra that, if detected, might imply that what evaporates isn't exactly what went in. Despite the elegance of the theory, mirror matter remains elusive. That is, perhaps, its most convincing trait. In a universe shaped by dark energy, structured by dark matter, and governed by quantum rules that defy classical intuition, the absence of evidence is not evidence of absence. It is the default. We live in a cosmos where only about 5% of the total mass energy is made of what we understand. The rest is mystery. And mirror matter, or more broadly, the mirror universe, offers not just a placeholder, but a coherent narrative for that vast unseen majority. The mirror universe hypothesis doesn't simply add particles. It adds an entire realm. It challenges our assumptions about uniqueness, about isolation, about what it means for something to be real if it cannot be seen. It reminds us that the observable might be just a sliver of what exists, a shimmer on the surface of a deeper ocean. Perhaps reality is stranger than we know, not because we lack tools to see it, but because it hides behind perfect symmetry, visible only in the mathematical shadows and quantum stutters that remain after every experiment. We are left with a possibility as humbling as it is exhilarating that we are not alone in the cosmos, not because of aliens or gods, but because the very structure of matter whispers of a twin, a silent counterpart, co-evolving with us, dancing in gravitational harmony, breathing mirror light into mirror lungs. And if one day we find the thread that binds our universe to its reflection through ghost particles, neutron transitions, or gravitational echoes, we may discover not just a new frontier of science, but a deeper understanding of symmetry, reality, and ourselves. If the mirror universe exists, hidden from us, except through the faint tug of gravity, then it poses an unavoidable question. Could the elusive dark matter, this invisible scaffolding of galaxies, be composed not of exotic, one-off particles, but of an entire mirror world? Could dark matter be mirror matter in disguise? This notion isn't just poetic. It's an increasingly serious contender among physicists seeking to reconcile what we observe with what must exist to make our models work. In the previous section, we explored the idea of a mirror universe, an unseen counterpart to our cosmos, where every particle has a mirror twin, where the laws of physics echo our own but remain cloaked in perfect invisibility. Now, we narrow our focus to a more tangible aspect, the role this hidden realm might play in shaping the very structure of the cosmos. Dark matter is one of modern science's great enigmas. It doesn't emit, reflect, or absorb light. It doesn't interact electromagnetically. Yet its gravitational influence is undeniable. Galaxies spin faster than they should. Clusters hold together more tightly than visible matter accounts for. And the cosmic web, the vast filamentary structure connecting galaxy superclusters, requires far more mass than telescopes can find. Roughly 27% of the universe's total energy budget is attributed to dark matter. But what is it? The standard assumption has long been that dark matter consists of some unknown particle, interacting massive particle, or an axion, or even primordial black holes. These candidates are still being hunted, but as each experiment yields null results, a different possibility grows more tempting: that dark matter is not some alien intruder, but a natural counterpart, a second cosmos made of mirror matter. This interpretation doesn't require inventing entirely new forces or breaking the standard model wide open. It simply extends the symmetries we already suspect may be incomplete. If a mirror version of our universe exists, then it must contain mirror atoms, mirror stars, mirror galaxies, and crucially, mirror mass. When cosmologists simulate the large-scale structure of the universe using only visible matter, the results are a poor match for what we observe. But add a dark component, massive, cold, and gravitationally active, and the cosmic filaments emerge with astonishing accuracy. The density fluctuations match the cosmic microwave background. The early formation of galaxies, the merging of clusters, all align. If mirror matter behaves gravitationally like normal matter, then it could fulfill the same role in these simulations. Yet mirror matter doesn't have to be entirely passive. The more sophisticated versions of the theory allow for minimal interactions between mirror particles and standard ones through what's known as kinetic mixing. For instance, mirror photons might mix weakly with our photons. Mirror electrons could have a tiny effective electric charge. These mixings would be extremely faint, but not zero, providing rare opportunities for detection. In practice, such effects might explain long-standing anomalies in dark matter detection experiments. Some detectors have registered unexplained seasonal variations in signal strength, patterns that don't correlate with known background noise. If Earth moves through a cloud of mirror matter, or if our planet passes near a region of enhanced mirror density in its orbit around the Sun, subtle interactions might occur. These anomalies, once dismissed as statistical flukes, are now being re-examined in light of the mirror hypothesis. But there's a deeper implication here. If mirror matter makes up dark matter, then it means the dark sector isn't sterile. It's dynamic. It could have its own nuclear processes, its own chemistry, perhaps even its own stars and galaxies, evolving over billions of years. In other words, dark matter may not just be matter, it may be structure. This reframes the cosmic picture entirely. Traditionally, dark matter is depicted as cold and dead, a kind of inert ballast keeping the universe from flying apart. But mirror matter introduces a far richer possibility that the cosmos is not silent and solitary, but dual-layered with two parallel evolutions running concurrently. While we observe galaxies forming, merging, and dying in visible light, a second history may be playing out invisibly, stars collapsing into mirror supernova, mirror neutron stars spiraling inward, perhaps even mirror life gazing out into their sky, equally puzzled by the hidden gravity shaping their world. If that sounds speculative, consider this. Recent gravitational wave detections have uncovered mergers that are difficult to explain using standard models. Black holes with masses too large or too small to easily form from known stellar processes. Could some of these events originate from the mirror sector, their gravitational waves bleeding into our realm, while their matter remains unseen? Even galaxy rotation curves, one of the key evidences for dark matter, might find fresh interpretation. Mirror matter could form a diffuse spherical halo around galaxies, slowing their outermost stars. But unlike exotic WIMPs, mirror matter might cool and condense, forming substructure within these halos, adding complexity to their shape and behavior. That could explain some of the scatter and variation seen in different galactic environments. Despite its elegance, mirror dark matter remains unproven. Its detectability hinges on the faintest of mixings, interactions at the edge of technological feasibility. Yet this is not unusual in physics. The neutrino took decades to detect after its prediction. The Higgs boson was theorized in the 1960s and only confirmed in 2012. Science moves forward, not only by confirming the obvious, but by daring to peer into the unseen. Perhaps the most haunting implication of mirror matter is this, that the great cosmic silence, the absence of alien signals, of meaningful contact, may not be due to emptiness, but to blindness. We may not be alone, but merely separated by a veil of non-interaction, where the stars of another world shine with mirror light, undetectable by our instruments. In the dark, they may see us as we see them, not at all. As we probe deeper into the universe, building ever more sensitive instruments and refining our theories, the question remains, will we one day catch a flicker of that hidden structure? A gravitational echo, a mirror spark, a signal from the other side. If dark matter is mirror matter, then the answer to one of the universe's most pressing mysteries is not only within reach, it's already all around us, hiding in plain gravitational sight. If mirror matter truly fills the universe as the hidden form of dark matter, then the most pressing question becomes, how do we find it? We've spent decades building massive detectors and powerful telescopes to understand the visible cosmos. But if much of the universe is built from something invisible, untouchable, and only faintly gravitational, how do we even begin the hunt? The idea that mirror matter could be dark matter is not just a theory, it's an invitation to look again at all the strange things we've already seen and all the mysteries still unexplained. It tells us to search more carefully, not just for what's missing, but for what might be hiding right next to us, just out of reach. Unlike many dark matter candidates that are thought to be completely alien to the known particles, mirror matter is familiar in a strange way. It mirrors what we know. That makes it unique. If it exists, it has its own atoms, its own light, its own chemistry, and possibly even its own stars and planets. But because it doesn't interact with our light or our atoms in the usual way, it's nearly impossible to detect directly. Still, there might be cracks in the wall, tiny windows through which we can catch a glimpse of this shadowy world. One of the most promising methods involves looking for something called kinetic mixing. This is a theoretical bridge between our world and the mirror world. It suggests that mirror photons, The particles that carry mirror light could slightly mix with our photons. If that's true, then under the right conditions, mirror particles might interact just a little with our world. Not enough to see them in a microscope or a telescope, but maybe enough to register in a highly sensitive detector. Some experiments are already designed to pick up rare and weak signals, experiments built for other dark matter candidates like WIMPs. But these detectors might also be sensitive to mirror matter, especially if it interacts with ordinary matter through even the tiniest charge. If a mirror atom bumps into a regular atom underground, it could produce a signal, a tiny flash of light, a small release of energy, a clue. Interestingly, there have already been some strange results in dark matter experiments. It remains one of the biggest open questions in the search for dark matter. Could mirror matter be responsible for the unexplained signals? Another idea is to search for gravitational anomalies. Since mirror matter still feels gravity, large amounts of it could bend light and pull on visible matter. By carefully observing the movement of stars in galaxies, the bending of light around galaxy clusters, and the behavior of cosmic structures, scientists can map out where the invisible mass lies. If mirror matter makes up dark matter, then it should be shaping these structures. Gravitational lensing is a particularly useful tool here. When light from a distant galaxy passes near a massive object, like a cluster of dark matter, it bends. This bending creates a lensing effect that can be measured. By studying the patterns of lensing, researchers can detect not just where the dark matter is, but how it's distributed. If mirror matter has different clustering behavior than other dark matter candidates, that difference might show up in the data. Beyond gravitational methods, some researchers are even exploring the possibility that mirror matter might exist within our own planet. The Earth might have collected mirror matter over billions of years. If so, it could be concentrated in the planet's core or hidden in underground pockets. There are even proposals to search for tiny disturbances or unusual events in deep underground labs, events that might be caused by mirror meteors or particles passing through the Earth. It might sound strange, but consider this. We already know that our detectors are good at spotting neutrinos, ghost-like particles that pass through the entire Earth without interacting. Mirror particles might behave in a similar way. And if they do, perhaps a new kind of detector, built specifically for them, could finally catch one in the act. In space, the search continues as well. Satellites like Gaia are mapping billions of stars, tracking their motion with incredible precision. If a mirror star or mirror planet passed near a regular star, it would cause a tiny wobble, an unexplained tug. Over time, enough of these anomalies could point to something invisible yet massive, quietly orbiting alongside us. Another line of research looks at cosmic rays, high-energy particles that constantly bombard Earth from space. If mirror matter can occasionally mix with regular matter, it might leave a signature in these cosmic showers. Some scientists are analyzing rare and unexplained cosmic ray events that don't fit normal patterns. Could these be signs of mirror particles colliding with our atmosphere? Even gravitational wave astronomy opens new doors. If mirror stars collide and produce gravitational waves, we might detect the ripples in space-time, but not see any light. A dark merger with no electromagnetic signal could be the fingerprint of the mirror world. There's also the possibility that mirror matter might help solve other puzzles. For instance, the Hubble tension, The disagreement over how fast the universe is expanding could be explained if the early universe had mirror radiation affecting the way it evolved. Some versions of the mirror matter theory include mirror neutrinos, which could subtly change the timeline of the cosmos. Studying the cosmic microwave background with extreme precision might one day reveal hints of this influence. Still, the search is far from easy. Mirror matter, by its nature, is slippery. It hides in gravity, it avoids light, and it leaves only whispers behind. It doesn't want to be found. But this challenge is what makes the hunt so exciting. Science thrives on the unknown, on puzzles that force us to rethink what we thought we knew. The discovery of mirror matter would change everything, from our understanding of the universe's makeup to the possibility of parallel structures, maybe even parallel life. Imagine a breakthrough where a single particle, detected deep underground, proves the existence of a hidden universe. Or a wobble in a distant star's orbit points to an unseen companion that no telescope can see. These small clues, stitched together over time, could uncover one of the universe's greatest secrets. The search for mirror matter is still in its early days. It's a journey full of dead ends, false alarms, and long nights of data analysis. But the reward could be enormous. The unveiling of a cosmic twin, the solving of the dark matter mystery, and the realization that we are only one half of the universe's grand design. As new technologies emerge, and as we learn to listen more carefully to the silence between the stars, the hidden presence of mirror matter may eventually come into focus. Until then, we continue the hunt, not just for particles, but for the reflection of everything we know hiding in plain sight. PARTG Mirror Life? The ultimate enigma. If mirror matter truly exists, then it's not just the physics and astronomy that shift. It's the very foundation of what we consider possible. Because if the mirror world is more than a scattering of invisible particles, if it mirrors not just atoms, but complexity itself, then a bold question arises: could mirror matter host life? The idea may seem like science fiction at first glance. Yet, if the laws of mirror physics allow for stable atoms, mirror chemistry, and mirror stars that forge elements just like our own, then there's no clear reason why complexity couldn't arise. If mirror hydrogen and mirror oxygen can bind, if mirror carbon can form the backbone of mirror molecules, then the door opens to mirror biology. Evolution, after all, is a process driven by physics and chemistry. If those processes have their counterparts in a parallel world, then life might have bloomed there too, quietly, invisibly, but perhaps as richly as it has here. And the implications of such life, mirror life, are staggering. Would it be conscious like us? Would it ask questions about its own universe, about meaning and origins, just as we do? Or would it be utterly alien in form and thought, living in the same cosmic space, yet unable to ever know that another version of existence is occurring, layered atop its own reality? In a way, the question is both physical and philosophical. Mirror life wouldn't need to be magical or supernatural. It could be entirely natural, just hidden behind a barrier of non-interaction. A parallel biosphere, evolving under the same universal clock, but walled off from our perception. The idea that evolution and life are not unique to our visible atoms, but are phenomena that emerge from complex systems, wherever they may be, suggests a deeply profound symmetry in nature. Imagine, for a moment, A mirror Earth. Not a perfect reflection, but a world orbiting a mirror sun, built from mirror atoms, layered in mirror clouds and mirror oceans. Its creatures may never touch our light. Its plants may never grow in the same electromagnetic spectrum, but its ecosystems could be complex. Its inhabitants could build, wonder, imagine. And just like us, they might be staring into the dark sky, trying to understand what lies beyond. This raises another striking question. If mirror life exists, could it ever interact with us? The sad truth is, probably not directly. The weak interaction between mirror matter and ordinary matter means that even if we stood in the same space as a mirror person, we would never see them, hear them, or feel their presence. It would be like coexisting with ghosts, present in mass, but absent in every other way. Their world could be bustling, vibrant, layered with civilization, yet to us, it would seem like empty space. But maybe, just maybe, there are rare windows, fleeting cracks in the wall where interaction is possible. Theoretical models allow for portals or transitions under extreme energy or quantum conditions. If mirror matter can mix, even subtly, with regular matter under special circumstances, then it's possible that signals, or even consciousness, might someday bridge the divide. This isn't just speculative fiction. It's a scientific frontier where quantum entanglement, oscillation, or exotic field interactions might offer a handshake across universes. Of course, the science of life is more than just particles. Life is structure, complexity, emergence. It's about metabolism, replication, and evolution. So, could mirror molecules fold into mirror proteins? Could mirror DNA code for mirror enzymes? Could mirror cells divide, specialize, and eventually form conscious brains? Current models suggest yes, in principle. If mirror chemistry is stable, and mirror planets exist with mirror oceans and energy sources, then prebiotic chemistry could take root. Life might begin, not just once in our universe, but twice, parallel to each other, with each unaware of the other's flourishing. Now, take a step further. Could we one day detect this mirror life, not by direct contact, but by indirect effects? Some speculate that mirror microorganisms, if they somehow leaked into our environment through a micro-interaction portal, might behave oddly. Their presence might not be detectable through conventional microscopy, but perhaps through gravitational anomalies or strange gaps in biological or chemical reactions, phenomena that don't fit traditional models. Could some unexplained biological events, such as unexplained mass losses in biological tissue experiments or unexplained interference in quantum systems, be hints of an invisible biosphere brushing against our own? These ideas are controversial and not supported by mainstream evidence, but they are not beyond theoretical consideration. The more we explore quantum foundations, the more our understanding of the impossible shifts. Philosophically, mirror life forces us to rethink everything. If the universe supports two kinds of matter, and possibly two kinds of life, then we are no longer alone, not in the cosmic sense, but in the metaphysical sense. The idea of life being unique, or even sacred, takes on a different form. Consciousness may not be a one-time cosmic accident, but a mirrored outcome of the universe's deep symmetry. It also invites comparisons to ancient concepts, duality, balance, reflection. Across many cultures and philosophies, from the yin and yang of Taoism to the Platonic world of forms, The idea of a hidden, mirrored truth has echoed for centuries. Mirror life makes that metaphor a possible reality. Science fiction has long played with these themes. Parallel Earths, invisible civilizations, entities just beyond the veil of detection. But science itself now whispers that perhaps this isn't fiction at all, just undiscovered physics. Would mirror beings have their own science? Could they be searching for us too, theorizing the possibility of ordinary matter as a missing puzzle piece in their universe? Perhaps to them, we are the dark matter. Perhaps they wonder why some stars wobble inexplicably, or why their gravitational maps don't add up. Perhaps they, too, have built detectors, hoping to hear a whisper from the other side. The enigma of mirror life doesn't end in the lab. It spirals out into the cosmos, into the heart of meaning itself. If one universe can give birth to life, and a second, mirrored one can do the same, then the universe is not just hospitable, it is fertile, duplicative, perhaps even recursive. In the end, we are left with a question that is both thrilling and haunting. What if we are not the only intelligence looking into the dark? What if someone or something on the other side is peering back? And if we ever find a way to reach across that boundary, to make contact, the greatest discovery in human history may not come from another galaxy, but from the invisible twin of our own. If mirror life is possible, then what about mirror minds? It's one thing to imagine mirror matter forming planets, oceans, and even life. But what if it goes further? If it mirrors not only biology, but consciousness itself? Could there be, somewhere out there, or perhaps even overlapping this very room, a mirror version of you? Not just a body, but a self, a mind, a consciousness. At first, this idea feels more like philosophy than science. But modern physics, especially quantum physics, has a strange way of making the impossible feel plausible. Because consciousness itself is already a mystery. We know the brain is made of matter. Neurons fire, chemicals flow, and somehow we experience thought, memory, and awareness. But how this physical system gives rise to subjective experience, the inner movie of the mind, is one of the greatest unsolved puzzles in science. It's called the hard problem of consciousness. Now imagine that mirror matter doesn't just parallel physical forms, but also supports complex neural structures. Imagine a mirror brain, quietly thinking in the dark. Could it give rise to a mirror consciousness? And if so, could it be connected to us in ways we don't yet understand? This brings us to a bold, speculative frontier: quantum consciousness and the mirror self. Some researchers have proposed that quantum processes might play a fundamental role in the emergence of consciousness. The Penrose-Hameroff model, for instance, suggests that consciousness arises from quantum vibrations inside microtubules, tiny structures within neurons. While this theory remains controversial, it opens the door to a staggering possibility that our minds may not be entirely classical systems. If consciousness is partly quantum, then it may be subject to quantum phenomena like superposition, entanglement, and decoherence. And if that's true, then a strange possibility emerges. Could your mind be quantum entangled with a mirror version of itself? Quantum entanglement is a phenomenon where two particles become linked in such a way that their states are interdependent, no matter the distance between them. Change one, and the other changes instantly, even across galaxies. It sounds like science fiction, but it's been experimentally verified over and over. What if, at the birth of your consciousness, perhaps during embryonic brain development, your mind branched into two quantum-linked systems, one in the ordinary world and one in the mirror world? These two selves would never directly interact, but they might be subtly correlated through quantum entanglement across the divide. This idea may seem outrageous, and yet it offers a strangely elegant explanation for some of our deepest mysteries. For example, consider dreams. We all dream. And in dreams, time, space, and identity blur. We meet people we've never known. We feel emotions with no clear cause. We fly, fall, wake up laughing or crying, sometimes with a deep sense that we've touched something else. Could dreams be moments where quantum information from the mirror mind bleeds into ours? Not as full communication, but as impressions, symbols, echoes, flashes. If the brain's quantum processes become less stable during REM sleep, perhaps mirror states influence the dream narrative, creating surreal, non-linear experiences. Then there's déjà vu, the eerie feeling that we've lived a moment before. Some scientists explain it as a misfire in memory processing. But could it also be a quantum echo, a flash from the mirror self, experiencing a slightly different path through the same event? And what about altered states, induced by meditation, psychedelics, or trauma? People often report feeling as if they've merged with something larger, seen parallel realities, or encountered shadow versions of themselves. Could these experiences be brushings up against the mirror self, a subconscious awareness of a being who shares your pattern, but not your path? Let's step back. To understand how mirror matter might link to consciousness, we need to revisit quantum interpretations. In the many worlds interpretation, every quantum event causes the universe to split, creating countless parallel realities. Every time a particle chooses between A or B, both happen, but in separate branches. In this view, there are endless versions of you, living out different outcomes. But the mirror matter hypothesis isn't the same. It doesn't multiply universes. It duplicates matter within this one. Instead of countless yous in alternate timelines, there may be just one mirror, you, coexisting in a shadow domain. Not a copy from a different choice, but asymmetric twin, bound to you by a deeper cosmic architecture. In hidden variable theories, like the one Einstein favored, quantum randomness is just the result of our ignorance. Hidden rules govern every outcome. Some theorists suggest that mirror matter could be the hidden variable, the missing half of quantum information that balances our visible world. This would mean that the strange, probabilistic nature of quantum mechanics isn't incomplete, it's just half the story. The other half lies in the mirror sector, shaping outcomes in a silent dance. Consciousness, then, may arise from both realms working in synchrony. And here's where things get personal. If consciousness is quantum, and quantum states can be entangled with mirror states, then your identity might not be entirely contained within your visible body. Part of you, your thoughts, feelings, intuitions, might arise from a quantum system that spans both sides of reality. Your mind might be a bridge between worlds. Could this explain phenomena like intuition? Or the feeling of knowing without reason? Might our mirror selves influence our decisions, not as external spirits, but as entangled partners in the process of thought? This isn't to say we should abandon neuroscience or leap into mysticism. The brain is still a biological machine, and its workings are increasingly well understood. But if quantum effects play even a minor role in its deepest functions, and if mirror matter truly exists, then we are faced with a staggering possibility. Consciousness may not be local. It may be distributed not just across brain regions, but across dimensions. It may involve entanglement with a mirror mind, running silently alongside our own. This could revolutionize not just physics, but philosophy, psychology, even spirituality. It might offer a new way to understand identity, death, and what it means to be conscious. Perhaps when we die, our biological processes cease, but the mirror self persists, carrying echoes of our mind into the darkness. Or perhaps both selves fade together, their entanglement collapsing with the final breath. We don't know. But this is the edge of science, the twilight where physics touches the mind and where mirror matter might be more than just a dark reflection. It might be the other half of what makes us human. And as we peer into the cosmos, searching for signals, particles, and meaning, perhaps the greatest mystery isn't out there, among the stars. If our consciousness could be quantum entangled with a mirror self, if there's another you in a hidden sector of the universe, then maybe, just maybe, mirror matter is not the end of the mystery. Maybe it's just the beginning. A window into something much bigger. A glimpse into the multiverse. Up to now, we've explored mirror matter as a hidden counterpart to our own universe, perfectly symmetric, interacting only through gravity or other subtle forces. But what if it's not just a strange quirk of physics? What if it's a clue? A hint that our universe, as we know it, is only one part of a much larger structure, something vast, layered, and multidimensional. In fact, the idea of a mirror world may point us toward a cosmic truth that modern physics has been circling for decades. That reality may be built like a multi-layered fabric. A multiverse. But before we leap too far, let's define what that really means. The term multiverse gets thrown around a lot. In science fiction, it often means parallel dimensions with alternate versions of Earth or different timelines, where history played out differently. But in theoretical physics, the concept is more nuanced and far stranger. There are actually multiple kinds of multiverse theories. In the many worlds interpretation of quantum mechanics, every quantum decision splits the universe into different branches, each representing a different outcome. Flip a coin, and one version of you sees heads, another sees tails. This isn't just hypothetical. Many physicists take this idea seriously as a way to make sense of quantum behavior. Then there's the cosmological multiverse, suggested by inflation theory. In this model, our universe is just one bubble in an infinite froth of expanding space. Each bubble may have its own laws of physics, particles, and even dimensions. We live in one bubble. But there could be countless others, just out of reach. And finally, there's the brain multiverse, proposed by string theory. This is where things get truly mind-bending. According to string theory, all particles are actually tiny, vibrating strings. The way they vibrate determines what kind of particle they are: electron, photon, quark, and so on. But for the math to work, string theory requires extra dimensions, more than the 3 of space and 1 of time we're familiar with. Some versions require 10 or even 11 dimensions. Most of these are thought to be curled up so small we can't detect them. But in brain theory, short for membrane, our universe is a three-dimensional surface, a brain floating in a higher dimensional space. And here's the twist. Other brains could exist right next to ours. Each one might hold its own version of physics, its own universe. We wouldn't see them unless they interacted through gravity or touched in just the right way. Now, think back to mirror matter. What if it doesn't just live in our universe, hidden from sight, but exists on a parallel brane, hovering millimeters away in a higher dimension? What if mirror matter is a ghost universe, separated not by distance, but by dimensional boundaries? This would explain why it's so hard to detect. Why it only seems to interact through gravity. Why it might feel so perfectly symmetrical, but still separate. Some researchers have even suggested that gravity might be leaking between branes. It's the one force that doesn't seem to fit neatly into the standard model of physics. It's much weaker than the other forces. Some physicists believe that's because gravity isn't confined to our brain. It spreads through the higher dimensional bulk. And if gravity can pass between branes, could entanglement stretch across dimensions? Could a quantum state in our universe be linked to a twin in the mirror brane? This brings us back to the question of boundaries. If quantum entanglement is real, and it is, then some part of the universe must be able to exist outside classical spacetime. That's where things become truly profound. Because in that case, boundaries between universes may not be as rigid as we think. They may be porous at the quantum level. This has huge implications, not just for physics, but for our entire understanding of existence. Because if mirror matter overlaps with ours at quantum boundaries, then the universe isn't a sealed-off system anymore. It's a network, a web of realities, possibly interacting in small but significant ways. The journey through mirror matter isn't just a scientific pursuit, it's a shift in how we define reality itself. As we stand at the edge of discovery, the most humbling truth emerges. We may not be the center of the universe, nor its full story, just one face of a hidden symmetry. The mirror may not just reflect us, it may complete us. And until we see both sides, the universe remains unfinished. The question is no longer what's out there, but what are we missing?